Welcome back to Understanding Epsilon Delta. In front of me I have a very large table of what seems to not make sense at first, but this will help you if you still don't know how to set up epsilon delta proofs properly. Again, this is all using the definition of the epsilon delta proof, and I'm going to write that here. For all epsilon greater than 0, there exists delta greater than 0 such that if x minus c is less than delta, or in other words, if x is within delta of c, then the function is within epsilon of its limit. Remember, you can think of delta as distance on the x-axis and epsilon as vertical error on the y-axis. But this gives you all the possible combinations of what limits are possible, assuming they exist. So, we're going to fill in this table piece by piece, as repetitive as it might sound, in order for us to properly understand how to set these proofs up. In one selection, we have what we let the y value bar be. We have either epsilon as a finite value or m as a threshold. On the horizontal, we have delta as the finite value or n as a threshold for limits at infinity. And then we have the x inequality and the y inequality and an example. So let's start with the limit as x goes to c of f of x equaling L. In this case, we choose an epsilon that's greater than 0. And we let delta greater than 0, the value we're going to choose, such that 0 is less than the absolute value of x minus c is less than delta. And the y inequality here is what I just mean that the distance between the function and its limit is within epsilon. All right? An example of that is going to be just any regular function. Let's just say limit as x goes to pi over 2 of sine x. All right? That'll equal 1. All right? And you can use epsilon delta at some point to prove that, but it's difficult, so we're not going to do that. All right, now let's look at the one-sided limit. Again, we choose epsilon greater than 0, all right? And we can actually fill these out one by one, but I'm going to do it in this way so we understand what's going on. Now, delta is also going to be greater than 0, but since it's the positive version, we just expand this inequality out to be negative delta less than x minus c is less than delta, and we just get x is less than c plus delta. Remember that if you draw a graph, and you have the c over here and c plus delta over here, when you're approaching from the right, you're just looking at the right-hand side values of the function. And so x is less than c plus delta because that's the maximum distance that x can be from c. All right? And now, because the L is finite, we just have the same f of x minus L is less than epsilon. An example of the right-hand limit is just the limit as x goes to 0 from the right of the square root of x is equal to 0. All right, and now I'm going to start speeding things up. And I'm sure you can fill this in yourself, but as soon as we see finite values of L, so finite limits, we already know that we're going to be dealing with epsilon. So we can say epsilon is greater than 0. All right? Now, delta will always be greater than 0 for finite x. So we have x, c from the negative. And here, when we deal with infinite limits, the delta value will still be positive. So we still have delta is here, delta greater than 0, and we can just fill out this table much quicker, right? Like this. All right? These are for one-sided cases and two-sided cases. All right? However, when we have delta or n for limits at infinity, where x goes to positive infinity, we have a threshold of n, and that will be greater than 0 for all positive cases. All right? Here's our n greater than 0. Here's a positive infinity, so we n greater than 0. And then here, positive infinity, right? Or that should be actually, that should be negative infinity, actually. That's my fault. Let's write that real quick. There you go. All right, so you have positive n's all around here. For the negative limit, we have n less than 0. Because the threshold, you want x to always be less than n when n is a large negative value. All right? Now, in the same case, whenever you see deltas, and this is from the left-hand side of the limit, so you see that this is going to be c minus delta is going to be less than x. All right? And the same situation happens when you have left-hand and right-hand side limits here. So c positive here will be x is less than c plus delta. And for the left-hand side, you have c minus delta is less than x. All right? Those are your setups in those situations. So let me just quickly reproduce these over here so we have more time to fill out the table. So, oh, that did not work. Okay, so we're going to have to do them by hand. So we have x is less than c plus delta over here. And I encourage you to fill this table out on your own as well. And again, here, because it's a two-sided limit, you have to do the full inequality here and here. All right? And now we can fill out this final one where it's c minus delta is less than x. Okay. And then for the inequality for the x value, for positive infinity, remember, it's always x being greater than n. For negative infinity, it's always x being less than n. So now you can see the pattern here. So we have x less than n, x greater than n, and x less than n. All right. Now let's jump back to epsilons real quick. If the epsilon is positive infinity, well, actually we don't have epsilon anymore. We have n, or m. So m is now greater than 0 as a vertical threshold. For negative infinity, m is less than 0. So we can just do the same over here, like this. And we can just keep reproducing this, like this. Because remember, whenever you're dealing with positive infinity as the answer to your limit, it's always going to be m, and it's going to be greater than 0, because that's the threshold you always want your function to exceed. Okay. Now, the y inequality for all the epsilon cases will always be the function's distance from its limit is within epsilon. So here's our example here, and I already see that I missed an absolute value bar. We'll just add those in later, so no worries there. So here we go. All right, and now I'm gonna just finish reproducing the rest of those. Again, whenever the L is a finite limit, you always want to be using epsilons, and so you have, in this situation, you have infinity everywhere, so you basically don't need the epsilons anymore. So we filled out all the epsilons that we needed to fill out here. Okay, so how about positive infinity? Well, remember that whenever x is greater than n, that implies that the f of x function is going to be greater than m, and if it's negative, f of x is less than m. So remember, m less than 0, m greater than 0, m less than 0. You want to reproduce these over here, so let's do that. So when f of x is greater than m, you have, I didn't select that, whoops. Let me just quickly do that. All right, so m greater than 0, put it here. And we're going to do the same thing, m greater than 0 over here. We have m greater than 0 over here. And we have m greater than 0 over here. All right? And for the m less than 0 cases, you already know what's coming. It's f of x is less than m, right? So for m, oh, that did not work again. That's a little frustrating. Don't worry, we'll fill this chart out in time for you to get back to whatever you were doing before. All right, f of x is less than m, and then we have f of x is less than m over here, and f of x is less than m, and it's less than m. Remember, this is all the possible mix and match combinations of epsilon delta setups. And that's really what these are. You can mix and match these as much as you need. And there you go. So if I ask you, what is your setup with definitions of epsilon delta for limit as x goes to c of f of x is equal to positive infinity, you can say for all m greater than 0, there exists a delta greater than 0 such that when x is delta within c, that the value of f of x has to exceed that threshold of m. All right, and now let's quickly go through some examples. So the limit as x goes to c from the negative of f of x equals L. Okay, so let's take the example of the limit as x approaches 2 from the right of the square root of the negative square root of x minus 2. Okay, what does that mean? Or actually, you know what? Let's do a bit simpler example. Let's say the limit as x goes to, let's see, what can we think of? We can say 0 from the left of the root of negative x is equal to 0. Remember, the root of negative x will just flip it across the y-axis. So that means that when you plug in really, really small values of negative numbers, like negative 0.0001, this will become positive and it'll become well-defined and it'll approach 0. Okay, now let's take a look at limit as x goes to positive infinity of f of x is equal to L. In the last video, I mentioned arctan. So let's use the same function. The limit as x goes to positive infinity of the function arctan of x will approach pi over 2. All right, and if you look at the graph of arctan, you can see that. All right, likewise, since arctan is an odd function, the limit as x goes to negative infinity of arctan of x will be negative pi over 2. So here you go, convergent values, and this is how you'd use epsilon delta to prove it. All right, now for x approaches positive infinity equals positive infinity, well, that's pretty obvious. Any function that is infinity at infinity will work. So we can say limit as x goes to positive infinity of just x is equal to positive infinity. And for the negative case, we can just use negative x. So limit as x goes to, well, as x goes to negative infinity of regular x, right, that'll be negative infinity. Oh, whoops, equals negative infinity. All right, how about as x goes to positive infinity of f of x equals negative infinity? Well, how about the limit as x goes to, we said, positive infinity of the function negative x squared? Then this will just be an infinitely large value, but it's negative, so this will equal negative infinity. And how about the limit as x goes to negative infinity being positive infinity? So the limit as x goes to negative infinity of, say, negative x cubed, that'll be positive infinity. All right, and I encourage you to graph these and figure them out on your own. So the limit as x goes to c of f of x is equal to positive infinity. Well, for example, we can say the limit as x goes to 0 of 1 over x squared is equal to positive infinity. And the limit as x goes to 0 of, say, negative 1 over x to the fourth, well, that's equal to negative infinity because it's a negative flip. Okay, how about c positive equals positive infinity? Well, we can say the limit as x goes to 0 from the right of 1 over x is equal to positive infinity. And in the last video, we actually used this example and used the setup of epsilon delta to prove that. How about c from the negative? So c from the negative equals negative infinity. Well, we can say the limit as x goes to 0 from the left of 1 over x is negative infinity. Remember, if you graph that function, 1 over x, you've got positive infinity as x goes to 0 from the right, and negative infinity as x goes to 0 from the left. And since those limits don't match up, obviously the limit does not exist, and so the function is actually obviously undefined. Okay, how about the limit as x goes to c from the right is negative infinity? Well, we've also encountered this before. The limit as x goes to 0 from the right of the natural log of x is equal to negative infinity. Remember that the graph looks like this. So as we go to 0 of the log, we get negative infinity. And how about the limit as x goes to c from the left is equal to positive infinity? Well, what function can we use for this? Well, let's just use the log of negative x. So the limit as x goes to 0 from the left of log of negative x will be equal to, or sorry, not that, because that's supposed to equal positive infinity. So let's hope that you caught that mistake before I did. So again, we're asked to show that the limit as x goes to some value of c from the left is equal to positive infinity. So we can use actually negative 1 over x. So the limit as x goes to 0 from the left of negative 1 over x is equal to positive infinity. All right, because again, if you plug in really, really small negative values, these negatives will cancel out, and you'll get a large positive value. So again, negative 1 over x looks like this when you graph it. It's just a flip of the original, so you get this. All right, I hope that this table is helpful for you in understanding how to set up epsilon delta proofs, because sometimes you don't want to feel like you've understood this proof, and then when someone gives you the limit as x goes to 0 from the right or the left, and you don't know what to do and how to set that up because you're thrown off, right? This table gives you all the possible mix and match combinations of epsilon delta proofs and how to set them up so you can have no trouble whatsoever. So I hope that this video helps you understand epsilon delta and get one step closer to mastering epsilon delta. We're going to have some more videos on the limit rules and how to apply them, but for now, take a look at the tricky epsilon delta examples and see what you can learn from them. As I always say, the best way to learn epsilon delta, and this definitely was true in my experience, was from experience. The more you practice, the better you'll get at epsilon delta. Watch more videos online of how people solve them and see what tricks they use. These will all be really helpful and important in you finally understanding how to use epsilon delta and realizing it's actually not as bad as you once thought. Thanks a lot for watching this video. See you in the next one.